So I'm Jeremy, and I'll be presenting the DRAM Latency PUF, which is a mechanism for quickly evaluating physical unclonable functions by exploiting the latency-reliability trade-off in modern commodity DRAM devices. And so this was a work that was published and presented earlier this year in HPCA, which is an international symposium on high-performance computer architecture. So I'll start off with an executive summary. Our motivation is that we can authenticate a system via unique signatures if we can evaluate a physical unclonable function or a PUF on it. And these signatures or PUF responses reflect inherent properties of the device, and therefore these responses are unique to the device that generated it. And so DRAM memory technology is a promising substrate for PUFs because they contain many small units which can be used to evaluate the PUFs, and they're very widely used in many modern computer systems. And so a DRAM PUF would enable you to essentially authenticate any system with DRAM device on it. So the current problem with DRAM PUFs today is that they're either very slow, require a DRAM reboot, or require additional custom hardware. And so to this end, our goal is to develop a novel and effective PUF for existing commodity DRAM devices with low latency evaluation time and low system interference across all operating temperatures. And so we propose a mechanism called the DRAM Latency PUF, which reduces DRAM access latency below reliable values and exploit the resulting error patterns as unique identifiers. And so in our evaluation, we experimentally characterized 223 real LPDDR4 DRAM devices. And we show that the DRAM Latency PUF satisfies all effective PUF requirements. And we also find that the DRAM Latency PUF can be evaluated in 88.2 milliseconds on average, regardless of the temperature. And this is a significant speed up compared to the prior DRAM PUFs available. Okay, so I'll first start off. I'll first expand upon the motivation. So we want a way to ensure that a system's components are not compromised. One example would be if an attacker came and swapped out a healthy part with a compromised part on your system during runtime in order to steal information. And so one way to detect such an attack is using a physical unclonable function, or a PUF, which is a function that we evaluate on a device to generate a unique signature on the device. And so we refer to the unique signature as a PUF response. And these are often used in challenge response pairs. And I'll show you an example of how a challenge response pair, or a CRP, works with this model where a trusted device wants to authenticate a device. And so first, the trusted device sends an input challenge X to the device, and the device takes that challenge and evaluates a PUF depending on what that input parameters were. It then responds with the PUF response according to the challenge, and the trusted device checks the PUF response and verifies that this device was within its trusted devices, set of trusted devices. And once it becomes authenticated, you can run privileged tasks on this device. And so first, we want to have a runtime accessible PUF, which can be quickly evaluated with minimal impact on concurrently running applications. And we want it to be able to protect against attacks where that includes swapping system components with malicious parts. And this can be done when we have a runtime accessible PUF that can be evaluated very quickly. So we can determine very quickly when a part was swapped. Secondly, DRAM is a promising substrate for evaluating PUFs because it is ubiquitous in modern systems. But unfortunately, the current DRAM PUFs are slow and get exponentially slower at lower temperatures. And this is because the mechanism that they use to evaluate their PUFs is inversely related to the temperature in terms of execution time. And so first, I'll talk about effective PUF characteristics. So using this model here where the trusted device wants to authenticate a DRAM device 0 in this cartoon, we want to make sure that a PUF is repeatable. And so this means that if we send a challenge 0 to the DRAM device, it'll respond with a PUF response 0. And then if we send the same challenge, it'll respond with the same exact PUF response again. The second characteristic is diffuseness, which means that you can send many challenges to this DRAM device, and it'll generate unique identifiers or unique PUF responses depending on the challenge that was sent to it. We also want uniform randomness, which means that all of these PUF responses that were generated with different challenges are different from each other, and essentially you cannot use multiple challenge response pairs to guess another challenge response pair. The fourth is uniqueness, where if you have multiple DRAM devices and you send the same challenge Z to each of them, they'll generate PUF responses that are all independent from each other. And so all of these PUF responses of different devices are significantly different, so we can identify which device generated it. The fifth is unclonability, which means that you can't take one of these DRAM devices and physically create a copy that would exhibit the same characteristics as the original device and essentially have the same challenge response pair space. And there are more analyses on these effective PUF characteristics in the paper if you're more interested. So we also want a runtime accessible PUF, and runtime accessible PUFs must have low latency, which means that each device can quickly generate a PUF response. And we also want low system interference, which means that PUF evaluation minimally affects performance of concurrently running applications. So now I'll go into our mechanism, DRAM latency PUF, but first I'll talk about DRAM operation that's necessary to understand our mechanism. So you've seen this many times today, but again, a DRAM cell is comprised of a capacitor and a transistor, and the capacitor holds the data in terms of charge. And the bit line is used to read out data from the capacitor, and the word line drives the access transistor such that data can move to and from the capacitor. So initially, the bit line is held at 0.5 VDD, and once you activate the word line or drive the word line high, the capacitor begins to share charge with the bit line. And after a certain point, when enough charge has been shared, the sense amplifier is enabled such that we can amplify the data that the sense amplifier sees on the bit line. And so after a certain point, you can read the data after the sense amplifier has amplified the data enough to an IO readable value. And the time in between activate and read is indicated by TRCD, which is a DRAM timing parameter. And so we could read these cells earlier when the bitline voltage actually reaches Vmin, which is the threshold for correctly reading the data. But we want to ensure that there's enough guard band for certain cells that might have different characteristics because of process manufacturing. And so some of these cells might reach Vmin at a later point in time than others. And so we characterize these different cells as strong or weak, depending on how fast they actually reach this Vmin threshold. So let's see what happens when we read with a reduced TRCD. Some of these cells are being read when they are actually below Vmin, and so they have a probability of failure. And the lower you read below Vmin, the higher your probability is to fail for a given cell. So the key idea uses these mechanisms. The key idea of the DRAM latency PUF is to reduce TRCD and then access a region of DRAM to create a unique identifier using the error patterns that were generated. And so a cell's latency failure probability is inherently related to random process variation from manufacturing. And we can provide repeatable and unique device signatures using these latency error patterns. So here's a cartoon of 21 bits here showing the process manufacturing variation. And the bigger cells are the stronger ones and the smaller ones are the weaker ones. And so the smaller ones have a high % chance to fail with a reduced TRCD, and the larger green ones have a low % chance to fail with a reduced TRCD. And so the key idea is to compose a PUF response using the DRAM cells that fail with a high probability. So now we'll talk about how to determine whether a single cell's location within a region should be included in a DRAM latency PUF response. So we decide to include the cell if it fails with a probability greater than a chosen threshold when accessed with a reduced TRCD. And so in this example, we choose a threshold of 50%. And so we read out the data n number of times, and then we determine the number of times that it fails. And here we see that it fails 60% of the time, so we do include it. And so the failure rate is greater than the chosen threshold, so the cell's location is included in the PUF response. So we've decided using characterization to induce latency failures 100 times and use a threshold of 10%, which essentially is just choosing the cells that fail greater than 10 times. And we do this for every cell in a contiguous 8 KB memory region that we refer to as a PUF memory segment. And so again, taking this example, we access it a bunch of times and then use that filter of 10% threshold and generate a PUF response. And this can be used to authenticate this device. So we can evaluate this DRAM latency PUF in only 88.2 milliseconds on average, regardless of the temperature. So now to give you a better understanding of what previous DRAM PUFs did, I will again talk about DRAM cell retention and then talk about their key idea in order to give you a better understanding of comparing the two works. So yeah, these cells, these slides might look familiar, but DRAM encodes information in leaky capacitors. And so we have these leakage mechanisms, and if enough charge leaks from the capacitor or into the capacitor, then the stored data is corrupted and there are failures. And so here we have the exponential decay of the charge, and Vmin indicates whether you can correctly read the cell or not. And so above it is a retention success, below is a retention failure, and the retention time is indicated by when that exponential decay crosses the Vmin threshold. And so again, DRAM has many cells, and prior work has actually showed that all these cells have unique retention times, and the retention times are uniformly distributed around DRAM. And so the prior work show that these retention failures can be used to uniquely identify a DRAM device. So the key idea of DRAM retention PUFs, which use retention failures for their unique identifiers, is that they generate a PUF response with locations of cells in a PUF memory segment that fail with a refresh interval n. And so here we have an animation where we wait a refresh interval of n and then record the cells that fail with the refresh interval n and ignore the others. So the pattern of retention failures across a segment of DRAM is unique to the device. And we use the best methods from prior work and optimize the retention PUF for our devices in order to fairly compare. So I'll talk about the weaknesses of the DRAM retention PUF now. So DRAM retention PUF evaluation is very long and leads to high system interference. And the long evaluation time is because most DRAM cells are actually pretty strong, and you need to wait for a long time for enough charge to drain from the capacitors in order to generate these PUFs. And this is especially true at low temperatures where DRAM cells could maybe hold their data for hours. Also, it has a high system interference, and this is because with current DRAM refresh can only be disabled at a channel granularity, which is between 0.5 gigabyte to 2 gigabytes on typical DRAM chips. And they must issue manual refreshes to maintain data correctness in the rest of the channels during the entire evaluation time of their small PUF memory segment. And those manual refreshes are going to the rest of the channel that's not contained in the PUF memory segment. And so manually refreshing DRAM consumes significant bandwidth on the DRAM bus. So the long evaluation time could be reduced in two ways. One is by increasing the temperature, which results in a higher rate of charge leakage. And so we can observe these failures faster. But it's difficult to control DRAM temperature in the field, and operating at high temperature is undesirable for the chip. And secondly, we could increase the PUF memory segment size so that we could observe more cells with low retention time in a PUF memory segment. But this results in a large PUF memory segment, which takes high DRAM capacity overhead. And so now I'll talk about the methodology we used to evaluate. We used our 223 2Y nanometer LPDDR4 DRAM devices, which were 2 gigabytes in size from all three manufacturers. And we used a thermally controlled testing chamber similar to the one in Reaper. And we had precise control over DRAM commands and timing parameters. And we tested retention time effects by disabling the refresh, and then we tested reduced latency effects by reducing the TRC timing parameter and inducing these failures. And so now I'll go into our results for the PUF evaluation of latency. So here on this graph, we have the temperature sweeping on the x-axis between our temperature range of 55 to 70 C. And on the y-axis, we have the evaluation time, and this is a log scale. So we first plot the DRAM latency PUF evaluation time, which is independent of the temperature. And here it's plotted as 88.2 milliseconds, which is the average evaluation time for our DRAM latency PUF. And this is using a 8 KB memory segment. We then look at, for the same PUF memory segment size for the DRAM retention PUF, and show that, and show the evaluation time for those PUFs. And so here at the lower temperatures, we see orders of magnitude of speed up, and at higher temperatures, we still see a pretty significant speed up compared to the previous PUF. We then try increasing the retention PUF segment size, and we still see significant speed up improvement. We increase the size yet again, and it's still an order of magnitude or more, regardless of the temperature. And so we repeat this analysis with all of our chips from manufacturers A, B, and C, and we see similar trends for regardless of the manufacturer. And so on average, the DRAM latency PUF is 102x or 860x based on the temperature, faster than the previous DRAM PUF with the same DRAM capacity overhead. And so in terms of system interference, during PUF evaluation on commodity devices, the DRAM retention PUF disables refresh at channel granularity and requires manual refreshes to all the rows in the channel, but not in the PUF memory segment, to prevent data corruption. And it has long evaluation times at low temperatures. On the other hand, the DRAM latency PUF does not require disabling refresh and has short evaluation time at any operating temperature. And there are other results in the paper that we don't discuss in this talk, but they include how the DRAM latency PUF meets the basic requirements for an effective PUF, a detailed analysis on devices of the 3 major DRAM manufacturers, the evaluation time of a PUF, and further discussion on optimizing retention PUFs, system interference of DRAM retention and latency PUFs, algorithm to quickly and evaluate the DRAM latency PUF, and design considerations for a DRAM latency PUF. Also, the DRAM latency PUF overhead analysis. So in summary, our motivation is that we want to be able to authenticate a system via unique signatures if we can, using a physical unclonable function or a PUF, and these signatures reflect the inherent properties of the device. And DRAM is a promising substrate for PUFs because it's widely used. And current DRAM PUFs are very slow, require DRAM reboot, or require additional custom hardware. And so we wanted to develop a novel and effective PUF for existing commodity DRAM devices with low latency evaluation time and low system interference across all operating temperatures. And so we proposed the DRAM latency PUF, which reduces DRAM access latency below reliable values and exploit the resulting error patterns as unique identifiers. So we evaluated many DRAM chips, and we found that the DRAM latency PUF can be evaluated in 88 milliseconds on average, regardless of the temperature. And that concluded my talk. So if there are any questions, I'll happily answer them. Okay. I guess that is the end of the lecture.